Right, thank you very much, Joel. So just to introduce myself briefly, I'm Pete Neal, the lecturer for the first year course in probability. And in particular, many years ago, I was an undergraduate at Nottingham, but then moved away as my career took me, and last summer returned to Nottingham, so completing the circle. So hopefully you should be able to see my screen. So what I'm going to do in this session is just give you sort of a taster of what a probability lecture will be like. So I'm going to work through a couple of concepts, one of them being conditional probability and the other one being expectation. So a number of these ideas, if you've done any A-level statistics and probability, might be familiar to you. So what's going to be my example? What's going to motivate what we go through? So amongst other things, I'm a football fan and have many times looked at collecting football stickers. So the current Panini Premier League football album contains 642 distinct stickers. So if I was to collect one sticker at a time, how many stickers do I need to collect before I obtain a duplicate? I get a sticker that I've already seen before. And the second question is, how many stickers do I need to collect in order to complete the whole album? Get all distinct 642 stickers. So these two questions have names. The first one is known as the birthday problem and is often framed in the way, what's the chance of having two people share a birthday in a group of a certain size? And the second question is known as the coupon collector problem. So we have a set of coupons, in this case stickers, that we want to collect. How many coupons or stickers do we need to collect until we've got at least one copy of every sticker? So what we're going to do is go through answering these two questions and introducing, if you like, the key probability ideas that we need to answer them. So what I'm going to start with is the idea of conditional probability. So we have a probability of an event. So we have a way of measuring how likely something is. For example, sticking with football, we might have the probability of Manchester City beating Chelsea. If we're thinking about the Champions League final coming up, and we might say we think there's a 0.6 probability or 60% chance of Man City winning. But then we get to half time and we find that Chelsea are winning 4-1. Then our chances or our beliefs or probability of Man City winning probably go down at this point. We're probably not very optimistic. So given the event, given that we know that at halftime they're losing, then we adjust our probability that they'll win the match overall. And this is known as conditional probability. So we look at the probability of an event A happening. So in this case, Man City winning, given, so conditioning upon the event that B has happened. They're losing at half time. So how we can express this mathematically is probability A given B. So we use a vertical line to divide between, on the left-hand side, the event we're interested in, and on the right-hand side, the event we're conditioning upon, if you like, the known information. And we can write this as the probability of the two events, both occurring. So the probability of Chelsea winning 4-1 at half-time, but Man City managing to come back and winning, divided by the probability that Chelsea are leading 4-1 at half-time. So an important thing here is what we need to make this fully defined is the probability of our event B to be non-zero. So we can't record any possible event there. For example, a football team scoring a negative number of goals. Okay, so how does that help us with the problem we're interested in. So when do I first get my first duplicate when I'm collecting stickers? So a question for you to have a go at answering is, and if you've got a phone, you can read the QR reader, or in the chat a web link should appear. What is the probability that the first 30 stickers that I receive are all different? So in the question, we've got a few options ranging from just a 10% chance that they're all different, 0.1, through to a 95% chance that they're all different. So what I'm going to do is just give a minute for people to sort of look at the possible answers. There's, I believe, 6 possible answers, and choose which one you think is right. I will then go through and show you which answer is correct. So the probabilities listed are 0.1, 0.25, so a quarter, 0.5, in other words, a half, 0.75, or 3/4, 0.9, or 9 out of 10, or 0.95, 19 out of 20. So we've got a couple of responses coming so far. I'll just give it a little bit longer. We're now up, getting quite a few. So I'm going to take it forward from here based on the answer I've got so far. So I've got no votes for 0.5 or 0.95, and my leader at the moment is 0.75, which has 4 votes. So this is really quite reassuring for me that I can teach you something, that nobody has come up with the correct answer, which is 0.5, or more precisely 0.50248. So what I want to look at is how we get at this answer. And to get the answer, we're just going to use conditional probability. So what we're going to start off with, as we did in the example with Man City and Chelsea, is start off with 2 events. My event A, the one I'm, if you like, interested in, is what's my chance that the first K stickers are distinct. They're all different. And in particular, I'm going to be interested in the case where K equals 30. Now my B, the thing I'm going to be conditioning on, is the event that the first K-1 stickers are distinct. So how's that going to be useful? So what we can note is that if my first K stickers are all different, if my first 30 stickers are all different, then certainly my first 29 stickers will have all been different to each other. So I can write the probability of A and B as just being equal to the probability of A. So in a mathematical sense, A is a subset of B. If A occurs, then B necessarily has already happened. And why is that useful is we can rewrite the expression we had for the conditional probability as the probability of A and B as being the probability of B, i.e. the first K-1 stickers are distinct, times by the probability of A given B. That is, my K sticker is a new one, given the first K-1 are all different. And we can then make use of what we had on the other side, which will give us the probability that we actually want, that they're all different. To look at the conditional probability, what we can do is just think of perhaps a simpler situation where we have 12 cards to collect, which I've denoted here. And so far we've collected 3, which I've coloured in red. So when we think about collecting the 4th card, if we want that one to be different to any we've got so far, then we can pick any of the 9 blue ones and we'll get a sticker, a coupon, which we haven't already got. Whereas if we are unlucky, a 1 in 4 chance or a 3 in 12 chance, we pick a red one, we've got one that we've already got. And we can extend this on to the situation we're interested in here, where we've got, rather than 12, we've got 642. So in that case, what we can say is the probability of A given B is we want to pick any of the 642 minus those stickers we've already got, K minus 1, out of the total of 642. And what we can then do is use this argument again and repeat it backwards. So we can say, well, we know the probability of having the first 30 being distinct, given the first 29 are distinct. We can then find the probability of the first 29 are distinct by looking at the conditional probability of the first 29 being distinct, given the first 28, and so on. And we can use a process which works backwards like this until we finally get back to the original sticker that we got. So in this way, we can write the probability of A, so that the first K or the first 30 stickers are distinct, as just a product. So just multiplying together these fractions, which all have denominator 642, the total number of stickers, but each numerator is decreasing by 1 each time as our chances or the number of options for a distinct sticker decreases. So what we can then do is work this through, and it's quite straightforward then to work out what's the probability the first duplicate occurs at a particular sticker. So what we have here is a plot of the probabilities, and we can see if we look at the y-axis, these go from 0 to 0.025, so about 1 in 40. So no particular outcome has a particularly high probability, but what we can see is the probabilities increase to a peak. So initially, it's quite likely that our stickers are distinct, but as we get more and more, there becomes more and more chances that we'll get a sticker we already have. And the peak is reached around 20, and then it starts to decrease. And the reason it starts to decrease is there's, by that point, a non-negligible chance that actually we've already seen a match. So whilst there's a good chance as we get higher and higher that a new sticker will be the same as one we've already got, we've already been in a situation where we've seen a duplicate. Alongside this, and this is what we have here, is a probability, what known as the probability mass function, probability of any particular outcome, is we can look at the cumulative distribution function. So the cumulative probability that we've got a duplicate by a certain number of stickers. So here we can see that by the time we've got 20 stickers, there's about a sort of 20-25% chance that we've got a duplicate. And certainly by the time we got to 60 stickers, it'd be really quite unlikely that all our stickers are distinct. There's about a sort of 95% chance that we'll have at least one duplicate. So as already mentioned, this is known as the birthday problem. So often it's phrased in terms of how likely is it in a group of a certain size we have 2 or more people sharing a birthday. And one example I like to make without this, sticking with the number 30, which I've chosen for the stickers, is a lot of school classes are consist of about 30 students. So what's the chance that in a class of 30 students, at least 2 of you will share a birthday? There's about a 70% chance of that happening. And this is under the assumption that each day of the year is equally likely, and we'll touch on at the end what happens if that's not the case. Another place where the birthday problem's really quite useful is in epidemic modelling. which is something I'm interested in and has got a lot more publicity in the last 12 months or so. And the birthday problem plays a sort of key role there. So in the initial stages of the disease, what we can do is model the disease using a simpler process, which is known as a birth-death process. Basically quoting infections equals birth and removals of individuals to death. And removal here could refer to, in extreme cases, death or recovery to the disease. But what we can do is come up with a good match between the two processes until we start trying to reinfect people who've already been infected. And that's a whole separate talk. And I believe one of my colleagues, K7, gave a talk about using maths to tackling diseases last week. So what I'm going to do now is just move on to the second problem I posed. So how many stickers do I need to collect to complete the album? So there's 642 stickers. So on average, how many will I need to buy to complete the collection, the album, and a chance for you to guess your number. So again, I put up the QR code and I'll give you a minute or so to have a go. I will make things a bit easier. I'll say the answer is a four-digit number. So somewhere between 1,000 and 9,999. So certainly apologies if you can hear the rain. The rain's cut in where I'm sat in my office at home. Right, so I'm still waiting for some responses, which might be the internet being slow at my end for this. So what I want to do is keep it open, let you put in your answers, and work through in that. I'm not going to give you the answer immediately like I did with the previous one. So how do we go about answering this problem? So the way we look at this is saying, well, suppose that I've already got K stickers. Let's say I've already got 100 stickers. How many more stickers do I need to collect to get to 101 different stickers? So to answer that, I'm going to use something called a geometric random variable. So a random variable is just a quantity which is random and is going to take values. In this case, it's just going to take integer values, or values 1, 2, 3, so on. And what we can do is define how many stickers do I need to collect to get my next new sticker. And the way to think about this is to think what happens when we collect our next sticker. Either it's going to be a sticker which is new to me, and that will count as a success because I've got one more towards my goal of completing the album, or it's a failure. It's a sticker I already have. So how many stickers do I need to get a success? Well, I can look at my probability of being successful. So again, as with a lot of the probabilities I've written down, my denominator is just how many different stickers I've got, which is 642. And the chances, or the number of stickers which are good for me, i.e. will be ones I haven't got before, will be 642 just minus k. So minus those I've already got. So we can then define our random variable x, and we can say, well, x is equal to n. So for example, n could be 3 if we have n minus 1 failures. So for example, 2 failures followed by a success. So I have my 100 stickers already. I get the next 2 stickers, and unfortunately they're both ones I've already got. Sticking with the football, they're both Arsenal players, so I don't want any more of those. And then I move on and get a new sticker, which is somebody I have not got before. And I'm not going to worry too much about which team that is. And the reason for singling out Arsenal is I've got a current 4th year project student looking into this in more detail, and he's an Arsenal fan, so he made a lot about that as we were going through. So what we can do here is we can work out, well, what's the probability, as I say, x equals 3. So I need 2, that will occur if I have fail, fail, success. So the probability of a fail is 1 minus p, so 1 minus the probability I'm successful, and we want n minus 1 of those. So we just do 1 minus p times 1 minus p, n minus 1 times. And then at the end there, as I say, we have a success. So probability multiplied by p. So I'm looking at, on average, how many times do I need to say how many do I need to collect to get all the stickers? So what I'm going to look at is what's the expectation of a geometric random variable. So what we can do here is give the definition of an expectation, or the average. So what this is given by is just summing up, adding up the probability that it takes n stickers multiplied by n. So we can write this out as 1 times p. So p will just be the probability we're successful first time, plus twice the probability that we have to wait till the second sticker. So that will be one failure followed by a success, and so on. And what we can see here is we have infinite many possibilities. I have to say, fortunately, it's unlikely that we're going to have to wait a very long time to get a new sticker, especially if we've only got 100 so far. But we have all these possibilities, and we can use the sum notation as a short way of writing this. So we can say, well, we're going to add up all the possibilities where our value n can start from 1, then go on to 2, and so on. And in this case, it could go all the way up to infinity. So we're going to work out what this expectation is. So what we need to do is be able to work out what this sum is. So adding up n times 1 minus p to the power n minus 1. So what we can do is look at a geometric series. So geometric series is just a series where every successive term is just some multiple of the previous term. And I'm going to look at the case where our geometric series is decreasing. So I'm going to take z to be between 0 and 1, because with probabilities, I want things to be positive. So if we add up, I'm going to start here at 0. We start the sum 0 to infinity of z to the power n. This is equal to 1 plus z squared, and so on. And we can show that this is equal to 1 divided by 1 minus z. So this is why we want z to lie between 0 and 1. It will actually extend to having 0 between minus 1 and 1. But as I say, I'm just interested in the case where z is positive. Is differentiate the expressions we have here. So if we think about z to the n, and if we differentiate that with respect to z, that will just give us n times z to the n minus 1. So what I can then do is look at writing this out. So I look at each of the terms I've got, 1 plus z squared, and differentiate each of them. So that will then be equal to 0 plus 1 plus 2z plus 3z squared, and so on. And if we look at the final term on the left-hand side, if we differentiate 1 over 1 minus z, we can then use the chain rule, and this will give us 1 over 1 minus z squared. So what we can then do is return to the expectation we wanted. So return to our geometric, and we can say, well, instead of z, what about if we used 1 minus p here? So we can write the expectation of x as p times this sum, and the sum is just given by what we had before in the previous line, with z replaced by 1 minus p. But 1 minus p will just be equal to p. So what we've got here is p divided by p squared, which is equal to 1 over p. So what we have with a geometric random variable is the average is, or the expectation is inversely proportional to the probability of success. So if we have a really high chance of being successful, we don't need to wait very long. Whereas conversely, if our probability of success is really small, on average, we're going to have to wait quite a long time for a success. So these make sense. We could think of it simple examples of this, such as how many times do we need to toss a coin before a head appears? So in that case, assuming we have a fair coin, p will just be equal to a half, and this tells us that on average we'll have to toss the coin twice. And moving on from coin tossing, which is one of probability lecturers' favourite things, to rolling dice. If we had a dice and we want to know how long on average or how many rolls we'll need to get a 6, again here we'll just have probability of getting a 6 as being 1 over 6. So on average it will take us 6 rolls of the dice to get a 6. So we can see that these answers sort of fit in with our intuition. So how is this going to help us with going back to our problem of how many stickers do we need to collect in total? What we can do then is say, well, we can write this as a sum of random variables. We can say, well, how many stickers do we need to collect until we get our first distinct sticker? Well, that's just going to be 1. Whatever sticker we get first, we won't have got another duplicate copy of. Then we can look at, well, how many more stickers do we need to get until we get a second sticker? And it's probably quite likely that the second sticker we'll get will be different from the first, and so on. And we can work through third, fourth, and so on, all the way down to 642. But by the time we get to 642, we've already got 641, so there's really quite a high chance of us getting a sticker we already have, so we're going to have to wait quite a while. So we can write this as a sum of random variables, a sum of geometric random variables, which all have different probabilities of success, depending upon how many stickers we already have. But a nice thing about expectations of random variables is that the average of the total is just adding up each of the individual averages. How long does it take me to get my first sticker, plus how long does it take me to get my second sticker, and so on. And we can work this out. So just using what we had on the previous slide, we can just take the probability of being successful at each stage, i.e. when we have 1 sticker or 2 stickers, the probability that our next sticker will be distinct, and just flip these over. So the expected number is given by 642 divided by 643 minus 1, plus 642 divided by 643 minus 2, and so on, all the way down to 642 divided by 643 minus 642. So we can see the first term here is 1. The second term is just a bit bigger than 1 plus 1 over 641. But by the time we get to the 642nd term, it's 642. And what we know is that on average, it's going to take us 642 stickers to collect the penultimate sticker in our set. So what about if we look at how many stickers it's going to take us to get to some particular value k? So we can look at a plot of this. So what I've got on the x-axis is how many distinct stickers we've got, starting with 1 and going up to 642, and on the y-axis how many stickers we require. And we can see that initially we quite rapidly get new stickers. Even up to 500, we would expect, if we collected 1,000 stickers in total, to have over 500 distinct ones. But then things really ramp up as we get towards the end, and getting a new sticker becomes harder and harder. And we can just actually list the averages, and what we can see is to collect all the stickers requires on average us going out and buying over 4,500 stickers. And we can see that to get to just 100, we'll on average need just over 100, or less than 100, 109. By the time we get to 200, we'll have got probably on average about 40 duplicates, and so on. And one thing which sort of surprised me even now when I came to preparing the lecture is that it actually takes longer for us to collect the final 20 stickers on average as it does to collect the first 622. So even when we think we're nearly there, we're not even halfway there. So something to bear in mind. Now I've told you how many stickers you need. How much will it cost you is going to be the important question. And at 70 pence for a pack of 5 stickers, that works out at an average of £633 to complete the album. It should be noted that by the time you spent £200, you've probably got most of the stickers, and hopefully you can find some people to swap with some of your useful duplicates. So hopefully £600 odd represents a worst case scenario. We've looked at the expected number. As a probabilist, as people interested in randomness, it's interesting to look at the distribution. So we might be interested, well, how likely is it I will complete the album for £500? Or how likely is it going to cost me more than £1,000 to complete the album? So it's quite hard actually to work these out exactly, but what we can do is use simulation. In other words, get the computer to repeat the process and to estimate the probabilities. And what we get is there's about an 8.5% chance, probability 0.085, that you'll have completed the album for less than £500. And there's a just under 1% chance, probability 0.009, that it would cost you over £1,000. But as I say, hopefully you can find some friends who are also looking to collect. We'll go on eBay or your other favourite selling site and maybe pick up those missing ones cheaper than having to trawl through lots and lots of packs. And here we just give a histogram of the number of stickers required to complete the album. So my experiment involved 100,000 simulations, and if I'd have gone out and repeated this in real life, looked at how many times how much it would cost me with 100,000 completions of the albums, it would cost me about £63 million. So I'm glad the computer did the hard work for me. But what we can see is here that in over 25,000 of the simulations, so in over a quarter of the cases, what we require is between 4,000 and 4,500 stickers to complete the album. The fewest stickers required were somewhere between 2,500 and 3,000. And there was one case where I got particularly unlucky. I think it required about 12,000 stickers to finally complete the album. Okay, so just drawing things to a conclusion, just given a brief introduction to the birthday and coupon collection problems. So what have we used to get at the answers we want? Well, we've discussed the idea of conditional probability, looking at the probability of one event conditioned upon another. We made use of expectations or averages and introduced the geometric random variable. So this is a random variable which crops up in many situations in probability and proves to be very useful. Obviously, we've just scratched the surface with this problem. There's lots of interesting questions we could ask, such as, well, you've told me how many stickers I need to collect before I get a duplicate. How many do I need to collect before I get 3 which are the same, or 4? And rather than just collecting by myself, what about if I'm collecting with somebody else and we're looking to complete two sets? How many stickers on average will I need to buy? And finally, a sort of key assumption under what I've been saying is the assumption that all stickers are equally likely. What happens if some stickers are rarer than others? How does that affect things? And a simple thing to say here is if the stickers have different probabilities, you're going to get to a duplicate more quickly because on the whole, you're likely to get the more common stickers early on, i.e. duplication. And typically it will take you longer to complete the set of stickers, complete the album. So if there's some rare ones, that cost of £633 is only going up. So that brings me to a conclusion for today. Thank you for listening.